Welcome to the PySnpTools tutorial. So PySnpTools is an open source library. We originally created it for reading bed files, but now it's expanded. I think it'd be useful for other kinds of matrix data. I'm Kadie. I'm in Microsoft Research in the genomics research group, and I'll also be giving some background about what we do. To help me get an idea of who you are, I'd love a show of hands. So who works with genomic files like the PLINK Bed files and phenotype files? Okay, this will be really, well, even if you might, it'll be very relevant to you. Who uses NumPy arrays but with like some more pandas-like features? Good. You can answer affirmatively to more than one, by the way. Interested in kind of fast sets of integers on ranges? Good, that one actually surprises me, it's cool. Would like just to learn a bit more about genomics from a Python perspective? Good, we'll be covering that to a degree. Interested in particular the FaST-LMM program for doing Genome Wide Association Studies? Okay. Interested in just an example of what I hope is a nice Python library and its design? Good. And if we have time, interested in one opinion about what's good and bad about Python from someone who's been doing scientific programming in other languages for 19 years now, maybe longer. Okay. I had the instructions for how to install. There are live examples in an IPython notebook that you can download. You can find it by downloading a zip file, either from that tiny URL, or you can search the PySnpTools documentation and you can see the zip file. But it's okay if you don't do that now. I'm going to run the IPython notebook live, but if you can either do it yourself also, or you can just watch. It'll work out fine either way. So let me give a little bit of background on where I'm coming from. I'm in the genomics research group of Microsoft Research. We were very recently renamed from the eScience research group. Before that, we spun out of the machine learning and applied statistics research group. Considering that history, we've been creating and applying decision theory and machine learning for 20 years. I think one of our biggest things was out of our group spun out a product group, the spam filter group, which was one of the first spam filters, commercial spam filters, and is still the provider of spam filters for Hotmail, Outlook, and Exchange. Language-wise, we used to use C++ for our things that needed to be really fast, and VB for UIs. Then we switched to C# for both. For the last, and we make our C# faster by using MKL matrix libraries. The past 3 years we've been using Python. We still use a version of the MKL library that we get from Anaconda, and we also write a little bits of C++ code to make things faster where we see the need. Currently, most of our work is on creating new analysis tools. Typically, what we produce is open source and for biology, and we've got papers on the Genome Wide Association Studies and other topics in journals such as Science and Nature. Also, as being part of Microsoft, we advise and help Microsoft product groups, especially with respect to how we use Python or scientific programming or issues like that. And this is work done with a wide variety of collaborators, and you can see their names down there. My background is I have degrees in computer science and machine learning. I came to Microsoft as an internet programmer for a product group, but then 19 years ago transferred to research, and I've been doing scientific programming there ever since. And a plan for the morning, we've done the intro, and we're on the plan. We'll look at this is the equivalent number of PowerPoint slides. So we'll look at SnpReader, which is an exemplar of the PySnpTools, and that'll be about 32 slides or the equivalent in the IPython notebook to understand its design and features. Then we'll have 6 slides on PstReader, which generalizes SnpReader to any matrix, any numeric matrix. We'll look at another particular kind of PstReader called kernel-creation. We'll look at those integer sets with 4 slides. Then toward the end, we'll see FaST-LMM, and we'll talk about what it is and how it uses PySnpTools to find genome wide associations. If we have time, you can have 4 slides on my opinion about why Python is both a wonderful and a terrible language. And there'll be 1 slide in conclusion. And we're a small group, so feel free to ask questions. So first, let me give you an introduction to genetic data. If you had the sample data that comes in the zip file, you can look at now or later, if you look at it, it just has files like all.bed, all.bim, and all.fam, and they're just text files. I don't know how to point. Okay, good. The most interesting file is this is the bed format from the PLINK consortium, I guess. So the most interesting file in there is the bed file. It has columns and rows, say 1.5 million columns. Each one represents a DNA position, 1.5 million DNA positions that we call SNPs, places where DNA is known to vary between people. And then we might have the data for, say, 5,000 people. And that would be the rows, 0 to 5,000. At any intersection, we have the nucleotides, the A, the C, the T, or the G value that person 0 has at DNA location 0, SNP location 0. In this case, I've said this person has AA. You can see that for this first SNP, most people have AA. 1 from mom, 1 letter comes from dad. Some people have AT, and a few people might have TT. There's another file that goes along with this if you're reading bed format. It's the BIM file. It contains the names of all the DNA locations, which are just a string, and it has some additional information. It'll have the chromosome that a DNA location, SNP location appears on, 0 to chromosome 22, and it has 2 other numbers, which I didn't make up here, measuring genetic distance, where the DNA location is along the DNA. One thing that's a little peculiar about this kind of genomic data is individuals are identified with an ID. That's not unusual, but they're identified with a 2-part ID. The first part's called the family ID, and the second part is sometimes called the case ID. And together, the 2 of them provide a unique identifier. So a couple interesting things here. A lot of genomic work isn't from databases. It's just from these plain files. The matrix data may be too big for a computer's memory. So when we just have these 4 letters plus missing, then we only have 4 values, and this file format compresses that to 2 bits. Even at 2 bits, 1.5 million DNA locations by 5,000 people is almost 2 gig. And if we expand this out to be a real number, which we need to do for a lot of our learning and analysis, that becomes 8 bits, a full floating point number, and this will become 56 gig. And you can imagine this is 5,000 people. Well, what happens when we have 10,000 people, 20,000 people? Now we're talking 100 gig, 200 gig of memory. An important principle that we can kind of pick from the bed format is that compared to the size of the main data, the information about individuals and about SNPs is very small, 5,000 times smaller, 1,000,000 times smaller. So we really don't well, we'll see the consequences of that. Also, we can look at this and say you ought to be able to read data from this file, access the data randomly. It would be crazy to read it all in if all you need is a particular row or set of rows and columns. And this is something I hadn't really thought of. Usually you think of tabular data, of which this kind of follows, of just being the center part. But here we have this auxiliary data, the BIM file, data with genetic information and chromosome data. That's kind of interesting, and I think it's useful in other contexts to have kind of small amounts of data that go along with either the rows or the columns. So the first thing this library has to do is be able to read these bed files. So here we have a IPython notebook. The first cell, which I already ran, just sets up some things. And we call it, the format is, the readers are called SNP readers, but there's a different SNP reader for each file format that you're reading off disk. So the bed SNP reader, you say import bed, and then give the name of the file. That'll return the SNP reader, and then we can print the SNP reader. So let's see what that looks like. If we do that, we get the name of the reader, all.bed. What's interesting here, or what's important here, is that we haven't actually read any data at all so far. We can ask about the number of IIDs, individuals, or SNP IDs, which is the columns. We can ask for a list of the individual IDs, and we can ask for a list of the SNP IDs. If we do that, we see in this synthetic data set, so that we don't intrude on anybody's genetic privacy. So in this synthetic data set, we have 500 individuals, 5,000 SNPs. The first 3 IIDs are here. You can see they have the 2-part, the family and the case. And then here's a list of the SNPs. To answer these queries, we have read a little bit of data from the file, but we still haven't read the main matrix file. So that's another key. We assume that we can get information about the labels that we have on the rows and columns and the properties on the rows and columns basically for free, and that it's only the main data that we want to avoid reading for now. Finally, when we do want to read the data, there's a command on any SNP reader called read. The result of that is a SNP data. A SNP data is also a SNP reader, but it has an additional field. So we can see it's a SNP reader because after we create it, we can print it. It's the SNP data made from reading a bed file on this file. We can ask about these same properties. They match up as they did before. As I said, it has this, in addition, it has this val attribute. And if we print the first 7 of that, we see the actual numbers from the data. This is a regular NumPy array, floating NumPy array, and that means you can take the .val and do things like ask what are the mean of the values. And here the mean is 1.47. If all you want is to read data from a NumPy array, you don't have to do things in the steps I just showed. You can put it all together. You can create the bed, give the file, say to read, look at the val, and then do whatever else you want with it. You'll get the same answer. You might think that's kind of crazy. We'll talk about why we're doing it in 3 steps instead of 1 in just a second. You can also create the in-memory SNP data object from scratch. You don't have to necessarily get it by reading a SNP reader. So here we import SNP data, and to create it from scratch, you give it the IIDs, which are pairs of strings, the SIDs, which are strings, and then the val, which is something that can be converted to floats. And then we can take the 0.8. So let's go back to the PowerPoint. So in summary, with respect to bed files, the bed is the SNP reader for the bed format. You can see IID, IID count, SID count before reading any SNP data. No SNP data is read until you say read. The result of reading is a SNP data object, which has a val attribute, and you can create SNP data objects from scratch. And here you can see kind of a way to look at the data that's involved in a SNP data. And any SNP reader is the same, except it wouldn't have the .val. So you're looking at that and going, man, if all you wanted to do was read a bed file, why did we have to go through 3 steps? Why didn't you just say, I don't know, read bed or something? You wouldn't even need an object. There's a payoff. The reason we do it in 3 steps is because it facilitates reading subsets of the data and also reordering the data when we want the rows or columns in a different order. And let's look at the notebook to see how that works. So suppose we only want the data for one column, which is a SNP. We create a SNP reader for reading bed files, and then we create a new SNP reader that's our old SNP reader with array indexing. Now, if you're, this is the same array indexing that NumPy arrays use. Recall that everything before the comma tells what rows you want, and everything after the column tells what columns you want. A colon by itself means the whole thing, so we want all the rows, and a 0 means we want the 0th column. So now we have a new SNP reader called SNP0 reader. Let's print out what SNP0 reader is, its IID count, its SID count, and then what SIDs it has. So when we print out, we just do a print on it, we can see that it's kind of got a readable name. It can remind us what it is and where it came from. It still has the 100 cases, IIDs that we expected before, but now instead of 5,000 columns, it only has 1 column, and here's the label for that 1 column, the SID. So here's an interesting question. We've said we wanted to read just 1 column. What happens to our original SNP reader called SNPReader? The answer is it's unchanged. Now we have 2 things for reading from this file. One is set up to read all the data, and the second one is set up to read only 1 column. To actually read, we say snp0reader.read, and that gives us snp0 data. We can print that out. We can look at its dimensions, and we can look at some of its values. So we saw the name before, 500 by 1, and then here's the first 10 values from this column. What's the bed reader is smart because we only asked for 1 column. That's all it read, so it didn't have to load everything else into memory. So this should be straightforward. Suppose we want the IID at index position. We want basically the column with index 9. Sorry, the row with index 9. How would we do that? Well, in 1 line, we can give the file. We can say we want row 9. We can say we want all the columns. We can read it and print the value. And there how we read just one row. In some ways, well, okay. So now suppose we want the first 5 columns and the first 5 rows. Very straightforward. The notation in Python for all the whatever's up to but not including 5, so 0 through 4 is colon, and then the number that you want to stop on, so :5:5 specifies as the range of rows and columns. We read and print out, and we see our dimensions are 5. We can ask this object, what are the names of your rows, the IIDs? It shows us those. We can say, what are the names of your columns, the SNPs? It gives us those, and we can ask for all its data because we did the read, and we see all the numbers there. So the indexing of one reader to create a new reader, to to say that you only want to read a subset stacks. You can keep doing it. So here's an extreme example. SNP-reader A is a bed reader for all.bed. We tell it that we want to create a new reader B that's A, but the first 250 columns. Then from B, we want to create a third reader, which is reader B, but the first 10 rows, IIDs. And then finally from D, we want to take the reader that we got from C and take every other row and every other column. The notation for every other in Python is : 2. So let's print this fourth reader and look at its dimensions. So we print it, and it actually remembers all the ways that we got to it. We ask its dimensions. It's 5 by rows by 125 columns. We can, again, look at the IIDs that label each row. You can see you go now 0, 2, 4, 6, 8, because we did the every other. And this last step was we did a read and printed the first 10 values, and you can see them there. Yeah? The readers aren't even views. The readers are a promise that if you ask it to read, it will be able to read. But it doesn't pull any data or make any data accessible to you until you say .read.
So sort of a lazy evaluation.
Yes, you can think of it as a lazy evaluation. We'll see how to write in a few soon. You can do all the fancy indexing that NumPy supports. PySnpTools supports almost. To its credit, it actually supports some things that NumPy arrays don't support. And NumPy arrays, sometimes NumPy arrays will get mad at you if you try to do things on rows and columns at the same time. And in PySnpTools, you're always allowed to do that. Maybe I forgot to mention something important here. This fourth reader, it only ever went to disk for those final values that it needed. It didn't go through all 4 steps and read things and throw it away and read things and throw it away and read things and throw it away. It's compressed all 4 steps down into 1 step and read only the final values that were needed. Okay, back to fancy arrays. Instead of a single index for the row, or the colon, or the : 2, you can give a list of indexes. So that's a way that you can use this to reorder your rows. So here we're saying we want rows 4, 3, 2, 1, and 0 with a colon. Do a read, and it'll nicely. Now you have this new SNP data object, and the new SNP data object knows that its names for its rows are CID 4, P0, 3, 2, 1, and 0. So the labels will always track the data. You don't have to worry about them getting out of sync. We can take this SNP data and use a Boolean selection, another thing you'll see on NumPy arrays. And we can say we don't want the first thing, we do want the second, we do want the third, we don't want the fourth, we do want the fifth. These are which rows we want, and we want all the columns. So we took a SNP data array. Now we've got this thing, I call it 4321B. We can print it out. It turned, internally the name, instead of having the Booleans, turned it to indexes. And you can look at the 2 IIDs we've now asked for. So here's a question. This thing, we just did this Boolean indexing on a SNP data. So this thing that it produced, does it have a .val attribute or not? Well, let's have Python tell us. And the answer is no. If you take a SNP data and you select, use indexing to create a new reader, that's a reader, but no data actually gets read until you say read again. I'll say that again every time. Well, we'll see it in a moment. But the SNP data did have the data, the thing we're reading from does have all the data in memory, not on disk. So you might think, well, it seems inefficient to read from it again. There is a way to tell it when you do the read that it's okay to create a view, that is to share memory. So if we do the read, now we have SNP data 4321B, and look at the value, we get just the final 2 rows we asked for. By way of review, yeah?
At this point, there's data. When we say you okay,
Yeah.
then the data actually ready to the memory.
The read is what made the data go into memory. By saying view OK, you're telling it that it's OK if this new data that you've created shares memory with the thing that it read from. Yes. And it doesn't guarantee that it will share memory. Python's very opaque about when it will actually have 2 arrays that share memory and when they're separate from each other. So you don't really know for sure. Finally, negative indexing. By way of review, in Python, slicing notation, you have a start, a stop, and a step. A negative start means count from the end. A negative stop means count from the end. A negative step means count backwards. We do support this. Indexing in NumPy arrays, a -1 means the last item in an array. -2 means the second to last. I forgot to implement this. I plan to implement it soon. Sorry about that. And lists can also have negatives, and that's not implemented either. But it does work for slicing. So here is how you'd say I want the last 10 rows. I want a reader that will read the last 10 rows. So this is normal Python notation on top of these new things, the SNPReader. So looking at how we do the subsetting, we can use indexing on a reader to specify a new reader for just the subset of the data. Indexing is also useful for reordering rows and columns, the IDs and SIDs. Using indexing to create a subset reader doesn't change the original reader. Every read will give us fresh data unless we say view OK, in which case it's allowed to share data if it wants to. And subsets of subsets of subsets, indexing on top of indexing, all that's fine. The read will only read the final data to the degree that that's practical for it. So I promised that we would have access to some pandas-like features, and I haven't actually shown any so far. So let me demonstrate that. First, a few more options on read. We saw view OK. You can also, when you read data, you can tell it what order you want, whether you want your matrix laid out in Fortran order or C order. That's important sometimes when you need your data to be able to be read fast. And it also supports 8-bit floats, which is the default, or 32-bit floats, sometimes called singles. And the option for that is to set this D-type argument. So let me show. Flags is the NumPy array method that shows you the properties of a NumPy array. So after we do this read, we can see that by default things are in Fortran order. Well, that's the most relevant thing here. But if we ask for things in C order and float 32, we ask to create an array that's a single instead of a double. That's true. And here we see that things are in C order also. We saw earlier on that there was this additional information for every SNP DNA location called. So to get to that, it's a property, an attribute called pos for position. We can just look at it. Again, you can get this without having to read all the data. Yeah?
Pandas in
There's no limit. The question is how much data can a reader read?
Like you were mentioning, that you can read gigabytes of.
Yeah, it depends on your computer. So this laptop is very small, and I made sure all my examples would fit in it. But my work machine has 48 gig, and it can certainly go that big. It can be bigger than the indexing. The rows and columns can have more than 2 billion entries, I think. I'm not absolutely sure that, but gigabytes and gigabytes, if you have the memory.
So in Pandas, you have to have that memory to read, but with this thing, even if you don't have that much memory, it can swap around.
That's correct. So a lot of the
I'm looking for difference between Pandas and this thing.
yes, so a lot of genomics algorithms, maybe it's okay to process, well, we'll actually see an example of this. If we want to find how related all 5,000 people are to all other 5,000 people, and we would do that by doing some dot product of their 1.5 million DNA locations, there's a very straightforward way of doing that in batches. You don't need to read all the data at once. You can read one person's data at a time, or one SNP at a time, or 5,000, and this facilitates that. And in fact, your algorithms can have an option, if they're using these readers, to start blocking the data and only read the sections that they need at a time.
So this is built in this.
Yes. So I promised, so here's the closest we get to having pandas-like features. Since we have this attribute position that says what chromosome each DNA location is on, and we can access it without reading all of this giant SNP data, we can do things like say that we only want to read the data for everybody at only their chromosome 5 data. So first let's take a look at that position attribute and say that we want the data for all the people, the rows, but only the first column. And that gives us just the chromosome number. Now we can say, tell us, this is that same expression, tell us where that's equal 5. This is just a NumPy array thing. This isn't anything I created yet. So just a normal NumPy array, when you set it equal to a single value, it returns a Boolean array telling you on each element whether it's equal to 5 or not. So the first ones are all false and the last ones are true. Now we can take this array of bools and use it to index our columns. And that gives us a reader that will only read chromosome 5. And we can actually do the read. And if we do the read and then ask what's the position data for the thing that we've read, everything now is just chromosome 5. So we've selected just the things that we wanted, the columns that we wanted. And in one line, we could do that all in one line. So here we've read just chromosome 5 for everybody and printed out the value. Likewise, suppose you only want to read the individuals or the rows that you have the name for. Basically, you want to do a read by name instead of by index value. The way to do that is to create a list of the names that you want, and then there's a function called IID to index, which will take a row of a list of IIDs and return the index value. So here's 3 people. I put it through this, and it gives me back an array of the indexes values for these 3 people. And now we can use that array, and we've created a reader that will only read data for those 3 people. And we can do that in one line, of course. So here's the reader, and we've asked what people do you read, and it only reads the data for these 3 rows. And we can do both things. We can read just chromosome 5 for the 3 people of interest and say find the mean value, do the actual read, and then compute the mean using NumPy arrays. So to review, the additional methods and attributes. We can return things in either Fortran or C order, which is important for efficiency. We can return either doubles, which is the default, or singles. Maybe we don't need the higher precision and we want to save memory. Every SNP reader has a position attribute, which is an attribute on the columns that it has genetic info. It's available before we do any reads, and then we can, we can use IID to index and SID to index to turn names into indexes, and then we can do, so that's basically as close as we come to pandas, where we can do things by name and by value to get the rows that we want and columns. There was a question about how do we write data, and you've only seen me demonstrating this on one kind of file format, the bed format. So let's take a look at that. So in genomics, there's another very common data set with a rather weird name. People, if you look in the documentation, it's the PLINK alternative phenotype file. It's just a text file. Here's what it looks like if you just open it up. It's white space delimited. It's got the family ID and the case ID, so together these are the IID, and then there'll be multiple columns, at least one, I guess. Here there's just one. And this is the value of something that you measure. In genomics, this might be something like body mass index. It could be a Boolean about whether or not somebody has a disease. Pretty much anything like that. And for this format, we've got a different reader called Pheno, and it works just like Bed, except it knows how to read from this format. So Pheno, for this file, we can print it out, and we can ask for its attributes. So when we print it out, it reminds us what it is, and its attributes are it has data for 500 IIDs and only one. It's calling it an SID. It's better to think of this as a column, because it's not really a SNP now. It's just some other variable. We can ask what the list of column names are, SID, and it says it's Pheno1. And it's not really meaningful if we're measuring body mass index to say what's the genetic, what chromosome is the body mass index on. So it fills in that attribute just with not a number values. And if we want it to read from the file, we can read from it, and here we're just printing out the first 10 values. So that's an example of reading from a second file format. And now that we have two file formats, we might want to read from one and write to another. So we create a bed reader for reading the first 10 values from our bed file, and then we'll say pheno.write. So every one of these SNP reader classes like Pheno and Bed that know how to read data also have a write method, a static write method, and the syntax is the name of the file, and then you give them a SNP data to write. And if we do that, we can check the file exists. We can also convert this subset of the bed file and create a new bed file. When you write a bed file, you actually get a bed, a BIM, and a FAM. That works. We can create data on the fly. So we created our own SNP data, as we saw before, and then we wrote it into bed format. And that's all straightforward. There's also two additional SNP readers that are handy. One is called SnpNPZ. It uses the Python matrix, the NumPy array matrix format. It creates very small and fast to write and fast to read files. So it's sometimes the case that you'll want to write to NPZ just because it's, say you had a text file, you might want to read it in and then write it out if you're having to read it over and over again, because the NPZ format would be faster. HDF5 is a more general purpose file format that can store binary arrays, and we have a flavor of that that you can write to and read from. The nice thing about HDF5 is, like the bed format, it supports low memory access of rows and columns. Some of the other formats like phenotype, you can access things in random access, but underneath the covers it really just loads everything into memory because it doesn't know any better way to read those text files. So in summary, methods like bed and pheno and SNP NPZ and SNP HDF5 all have write methods. SNP data is our in-memory format. It doesn't have a write method. And FaST-LMM, when you do some indexing, that doesn't have a write method. And just to remind you, only SNP data has the val attribute. Yeah.
Write the file,
Yes.
not update in place.
It never updates in place. And, I mean, if you wrote over, it would, but it doesn't support that now. I could imagine an extension that did that. It would look like SNP data, but but when you wrote, it would write it all the way through. But that's not the way it works now.
That's because biology data.
Yeah, this biology data, we tend, especially if we're going to do big matrix operations, like eigenvalue decomposition or whatever, things have to all be in, at least big chunks need to be in memory.
Most of the time, I read only write once.
Yeah, and then we might write back over what we had before. So here's a question. Say you do have this genomics data, but you want to use it with somebody else's library, not my library. Like you just want to use some SCA Learn or some other libraries, just generic array libraries. Let's see how PySnpTools makes that straightforward. So one of the most common things you have to do is you have one data set that has everybody listed in one order, the bed file, say, and you have another data set that has everybody listed in a different order. But if you're going to put this into a NumPy method for, say, doing linear regression or any of the learning things, it needs the two arrays to have to have the rows in the same order. So in this example, we read all the bed data, but our phenotype data pretend we have only half the people and they're in backwards order. So that's what we're simulating here. So our bed reader knows about 500 people. Our phenotype reader only knows about 250. And the bed reader, they go 0, 1, 2, 3, 4, 5. And our phenotype reader, they're in backwards order. So how can we call some other, some kind of machine learning tool if our two arrays are going to have the data in different order? And the answer is there's a utility called intersect apply. You give it a list of SNP readers, our SNP reader, our phenotype reader, and it returns new SNP readers that still haven't read any data, but where the IDs will be intersected and in the same order. So I just asked it, verify that the ID lists from both of these new readers are the same, and indeed they are. And then we can read them. And here's our data from bed, and here's our data from phenotype. So let's see how to use this in NumPy's built-in one of its built-in linear regression methods. All we do is take, say, .val. That'll give the kind of independent variables that the built-in linear regression expects. And then we say .val, and that gives it the dependent variable. It outputs a bunch of things, but the first thing it outputs is the weight that it thinks you should put on each feature, in this case, each SNP value. And we can actually see how well this model fits the data that we trained it on by multiplying the SNP data with the dot product times these weights, and then just doing a plot. And we can see that at test on train, we're doing great. We're predicting it. We're just nailing it. Of course, test on train is usually bad idea. We really want to see is how well we do on new data. So suppose we have the second phenotype reader, and it's going to read the other half of the individuals. We again put it through intersect apply with the bed reader, and now we have the SNP reader for the bed for the genetic data and our feature. Now all lined up, we can read them. We can take the weights from before and do the dot product on this new data, and then we can plot the true values on this unseen data and the predicted values. And now we see that linear regression turns out to be a really bad idea if you have 5,000 variables and only 250 cases. I think there's one more section specific to genetic data, and then we'll look at broader topics. So in this section, we saw that intersect apply can intersect and reorder readers by IID. It works before reading the SNP data from disks, so it can be very efficient. I didn't show this, but it also works with none. It works with any number of SNP readers. You can pass in a none, and you'll just get a none back. Also, it can work with non-SNP readers. If you want to, you can just give it a tuple of an IID list and a NumPy array of values, and it'll return a new IID list and a new NumPy array. So that's how you can work with other kinds of data. It's fine to do this step where you kind of reconcile your data between, say, the thing you're predicting, your main data, your features, say, and your target. And then you can do other things like cross-validation and all that with indexing. And you still never have to read until the last minute. And we've seen how it can be useful with other tools. I tried to come up with a question that would motivate this small section. All I came up with was, hey, how do you do standardization in kernels? So this is a small section, really only of interest to genomics. So in genomics, it's basically a kind of feature cleaning that we do in genomics. You have all these SNPs, they have values 0, 1, or 2. You don't want one that has lots of 2s to have automatically more weight than one that just has values near 0. So what we commonly do is go through and find the mean and standard deviation of each of these SNPs, which are features, and we make them have 0 mean and standard deviation 1 by multiplying and adding 2 numbers to each one. That's called unit standardization. We can do that in one step. There's other kinds of standardization like beta standardized, so we've defined a bunch of those. Another thing that's interesting to do is we almost always want to find how related like our 5,000 or 10,000 people are to everyone else. That's such an important thing that it's got a built-in method called read kernel. Read kernel takes the standardizer. The reason it does that is because read kernel can work on a reader. You don't have to load your data into memory to create this this kernel that finds the matrix of how related everybody is to everybody else. And as I alluded to before, this is one case where we have a block size argument. So you can actually do this calculation, 20,000, 50,000 people related to each other, and you can do it in very low memory. And it will work, yeah. So standardization only works on SNP data, so you have to do a read before you standardize. It works in place, and that's for efficiency. So you have this .val array. When you standardize, it actually changes. It also will return, well, you can see that. There are other standardizers that are handy. Whoops. Kernels, read kernel will return a kernel data, something that we haven't, a data type we haven't really talked about, but you can know it has a .val property, and it does the SNP reading itself. When you don't want it requires you to give it a standardizer. If you don't really want to standardize, you just say, use the identity standardizer, and that's the one that does nothing. Okay, so those who are interested in more of the genomics, here's the generalization of SNPReader. It's called PstReader, and it works on more kinds of matrix data. So as before, the values we're dealing with are still going to be reals, either single or double. But now our rows are called row instead of IID, and they don't have to be two strings. They don't even have to be strings. They can be any number of things, numbers, strings, or whatever. Likewise, columns don't have to be identified with one string. You can identify it with any type you want, and it can have whatever width you want. Before we had genetic properties up here. Now you can have any number of those properties. They all have to have the same type, but it can be any type you want. And we didn't have any notion of properties on the, that was column properties. We didn't have any notion of column properties, sorry, row properties before. So now we can have row properties. And in fact, a SNPReader is a PstReader. So anywhere before where you set IID, you can also say row. And whoops. And kind of as you'd expect, where we had row count, IID count, you can now say row count in general. IID to index, you now say row to index. And that's our generalization to any other data type that still has to kind of fit this paradigm. So let's see an example of that. So every SNPReader is a PstReader. So we prove that by reading it in and then asking for row count and column count instead of IID count and SID count. Column property. You can also create a PST data on the fly from scratch. So now our rows, instead of being two strings, are just one string. Our columns are strings, our values, and we've created something new, a row property. In this case, each row has the capital letter of its index as its row property. And we can do all the things you'd expect. We can say we want a reader of this data that selects all the rows where the index is less than C alphabetically, and we can, and where we want the columns for Z and the column for Y. And we can do that all in one step. And it gives us a reader. And if we read that, then we've got our data read and all turned around the way we want it. And we can even look for the properties in the rows we just read. And I didn't define a column property in that on-the-fly data structure. So if you don't define one, it gives one with zero width. So it's defined, it just doesn't have any width. And we've got two new readers, PstNPZ and PstHDF5. And they work just the way you would expect, I would hope. So taking that in-memory thing we had before, we say .write, we write it. We can read it back in. We can write it to HDF5. We can read that back in. We can look at the values from the things we've been reading and writing back in, and they all match up as we'd expect. Yeah. PySnpTools. I just needed some initials to identify it. So when choosing these formats, the NPZ is good because I think it's the fastest binary format for arrays in Python for reading and writing. HDF5 is okay for speed and size, and it allows low memory random access. It's also readable by other programs if they can understand your schema. So these are almost the only PST readers that I've created. But if you have your own data formats, one difference between this way of doing things and Pandas or even NumPy is that it's extensible. It doesn't dictate a format. You take the formats that you already have and you write a reader. And once you have that reader, you can do all these other tricks. And writing a reader is straightforward. in the case where it's okay to load all the data into memory. Obviously, if you need to be able to access rows and columns in kind of random order in low memory, that's going to take some coding that's specific to whatever file format you have. We've done it for HDF5 and Bed. If you have another file format, you have to work that out. One slide on kernel-reader. Kernel-reader is just what you'd expect for representing this person-to-person information that we see in genomics. So there's two flavors of it. One, if the rows and column names just happen to be exactly the same, it will note that. Or they can be different. What's fun in the programs when using this, before I had this, I had to write my programs so they only accepted kernels, this relationship between people to people in one format. Either they'd be on file or they would be in memory. Now I can write my program so it doesn't care whether it's in memory or on file. Or what's kind of cool is there's even a kernel reader called snpkernel. It takes a snp reader and on the fly will create the kernel that's requested, but only when it's requested. So that's a way to get very low memory, and also some algorithms know how to work with kind of implicit kernels, and they can look at this and be optimized for that path. I'll talk a little bit more about that in a bit. Here's a summary of all the formats. We had PstReader, snpReader, and kernel-reader. These are all abstract. You don't actually create a class with these names. But under PstReader, we have PstData, NPZ, and HDF5. Under snpReader, we had all these. There's a few others that I didn't talk about. And under kernel-reader, there's these. And it's easy to create more. Just do the little bit of work to create a reader, and then you have access to all the other features. Okay, changing top. Yeah.
All the users, they all support doing data calculations on data bigger than your physical memory.
All the readers give you the syntax to pull out just the NumPy array that you really want at the last possible minute.
It's like if I'm doing cosine similarity of all my text feedback and I have millions of documents, and this document of metrics is like skewed.
Yes.
Do I do extra coding or this thing takes care of?
You have to make sure that you have a reader that can read your data format in random access the appropriate way. So I have that for my genomics data, my bed file. You need to make a reader for your like web page features or whatever it is. Yeah. So if you have a file format, or if you could create it in memory and then just write to PST, NPZ, or HDF5, that would work. But you probably do have to create one reader that gives you random access to your data. And then after that, you can use the rest of the tools to pull things in parts. And I should say, this has evolved. I mean, obviously, we started out with just a bed reader. And the bed reader didn't work for us when we needed to apply the same algorithms to phenotype data. And then we wanted to create some stuff in memory. And then we were running on a cluster, and the file format for the phenotype reader was too slow, so we wanted to cache it. And we kept having to special case it. With this, you write your program so they only have to know about one format, and it's up to and then the caller has freedom to provide whatever data is sensible for that run. In memory, on disk, compute it at the last minute, whatever. Okay, this is only a few slides, but I think it's kind of fun. Here would be the rude question to ask me. Why would I think it's a good idea to create another data structure for sets? Hopefully I can show that and justify it. So here's the kind of problem that I see all the time, and I actually saw problems like this, not just with genomics data, but with any data. So suppose I need to take the union of these two sets. The first set is integers 0 to 499 and 501 to 999. And my second set is the integer minus 20 and then 400 to 599. So here's how you would do that using the int range set class. You import it from PySnpTools utilities. You create an int range set. One way to do that is with this syntax, a string, commas separate ranges, colons give the start and stop for each range. The stop is exclusive, like is the convention in Python. Here's our second set. And then Python already has a set class that has all kinds of cool operators, including vertical bar, meaning set union. So we use that. We support all those. And we can print the union of the two sets. And it does a nice syntax here. It says the union is minus 20 plus the range 100 to 1,000, exclusive on the 1,000. This is a real set, not just a string, so we can say is 200 in the set? The answer is yes. Is minus 19 in the set? And the answer is no. We can do more complicated things with ranges. So this is a real problem. We know, say that we know that this range on the DNA is important, is the transcription range. It has something to do with generating a protein. But the actual parts of the data that really code for the protein are the green, here, here, and here. And we want to know what's left out, called the exons. And our file format is we get the name of a chromosome. We don't care about that. We get the start and last position of the coding of the whole transcription range. And then we get a list of the starts for each of these, exons. Those are the exons. And the last of each of the exons. So you have to do just some kind of normal parsing. Parse this on white space into the, well, just as you'd imagine. Turn them into numbers with the int function. The data format that was input here gave the last position, but in Python we usually want to go one past the last position, which in Python we normally call end. So we do that, and we can create a new set that is just the blue thing we had up there. And it'll say, yeah, it goes from here to there. We take those two lists of numbers and kind of do normal Python things to break them up, to split them. And now we'll get a list of the start positions, a list of the end positions. They should both be the same length, 3, and that assert is okay, so we're okay. And just built into Python is something called izip, which if you give it two lists, will return a tuple from the first position of the two lists, then the second, and then the third. And it does it on the fly. It doesn't have to allocate memory for a complete double list. We can take that range set we had before and do set subtraction for the output of izip, which is this iteration of tuples. And if we do that, it does just what we want. It gives us the two ranges that are left over after subtracting everything. And it's straightforward if we want it in a different format to go through the ranges and print them out nicely. So int range set is a drop-in replacement for the built-in set class. It does, I honestly believe it does everything. It does, that sets does. Set equality, membership, subset, superset, proper subset, symmetric difference, efficiently enumerating things backwards. There's a thing where you can delete a member of a set by position and get an error if it doesn't exist, or not get an error. That's just normal Python. And that's supported here. Also, it has a couple more efficient functions. Obviously, if you have things represented internally as ranges of integers, you can find the min and max very quickly. As I think Gauss or someone figured out, you can also find the sum of ranges of integers more efficiently than actually going through them all. So we do that. Whoops. So we support that. Important for genomics, the human genome goes up to about 3 billion positions. So that's too big to fit in a normal int. So this all works with the bigger longs, the larger ints that Python also supports. It's very fast and super memory efficient anytime you have rangy sets. They do have to be sets of integers. Integers are kind of special because if you, not only are they intervals, but they're intervals that you know when they connect, and you don't have to worry about, like on real numbers, whether the last little bit is included or not. And after you do all this, you can ask for ranges. You can ask for it back as ranges or the length of ranges and so on. And there's all kinds of nice ways to input the data. We saw this one. You can give it a new integer element with 3. You can give it a tuple, which means go 3 to 8, not including 8. You can use Python slice notation. And you can also give lists or enumerables of any of the preceding things. Yeah? So ints can only, in computer languages, can only hold integer values up to about 2 billion. But in genomics, we go into 3 billion just for humans, and one can imagine going even higher.
The int is like what, 4 bytes or 2 bytes?
It's whatever it is.
Or whatever.
I forgot what it is. I think it's 4 bytes.
So how about long then?
A long is twice as many bytes, and it goes, I don't know, into the trillions, I think. It's 2 billion times 2 billion is the largest long. It's very big. I've used this in non-genomics things where I've gotten reports back, and I've got lines back with numbers, and I wanted to see if anything had gotten dropped out. So I used this to accumulate all the integers I was getting back in lines, and then ask what was missing. And it can do that with a simple set subtraction and give it in a nice range format so it's easy to read. Okay. On a broader topic, let's talk about, I think, 8 slides on Genome Wide Association Studies, and in particular, a program from my group called FaST-LMM. So apparently, it's almost required by law for everyone doing a genomics talk to give this slide, which shows that although this is logarithmic scale on the left, even though computers have memory and all that has gotten cheaper by Moore's law, every 2.5 years, getting more power for the same price, the cost for sequencing your DNA is dropping much faster. And now it is down below $1,000. So where before it took, what do we say, more than $1 million to do the first person's DNA, now it's routine for everyone to get DNA. What's interesting is even though there are, for humans, 3 billion DNA locations, for most of them, they're the same for everyone in the world. And because they're the same, we don't really need to measure them when we're doing these kinds of studies. So we concentrate on trying to only measure the DNA locations that are known to vary between people. And that's less than 1/10 of 1%. Which means we only have millions of DNA locations that we need to measure to find differences. Genome Wide Association Studies, you hear about them in the news all the time. The general idea is you take a set of individuals and you have measurements of some trait. Do they have heart disease or not, glaucoma or not, what's their height? And then a set of these SNPs, the DNA locations, maybe 1 million of them for each person. And we try to find a list of the DNA locations that seem to be associated with the trait of interest, like making you more or less likely to get the disease. So there's a couple challenges here. The first, if we are testing each DNA location one at a time and we've got 1 million of them, and we're doing the kind of standard scientific thing of saying our p-value has to be greater than 0.05, that means we're going to get 25,000 false associations, just false hits. So somehow we have to control for that we're testing so many different things. Another problem, if you remember statistics, every statistics class you've had said, okay, the first thing we're going to do is assume that all our data is IID, individually independent of each other. So if we're finding the height of people in the US, we don't take people from just one region, we actually pick people randomly. Well, this genetic data, that's almost never the case. First, it's often very convenient to collect data from families, and you'd think it would actually be particularly useful to get the insight of families. And even if it wasn't for families, their populations, human populations are clumpy and in groups. So in no sense is the data that we do genetic work on independent, are the cases independent of each other. And the final problem is the data sets grow every year. So the first problem, there's kind of just straightforward statistics for multi-test corrections we can do. The second problem, instead of using tools like linear regression and logistic regression, we use a tool called a linear mixed model. A linear mixed model says, you know, we know exactly how related every pair of people in our data is because we have their DNA. We can just compute it. You just do a big dot product. Once we know that, there ought to be some way to factor that out. And that's what linear mixed models can do. They basically take data, they factor out the relatedness, and then you can just think of it as doing linear regression. Variables to independent variables to some dependent variable. The final problem, the data set's growing, was a big problem because the algorithms for doing linear mixed models were quadratic, went with the square or the cube in memory and time. But our algorithm, FaST-LMM, which we wrote about a few years ago in Nature Methods, is linear in the number of DNA locations and the number of individuals. There is a constant. We're working on that constant. It's actually getting better. And that means kind of the straightforward way of doing linear mixed models goes crazy. The best previous method still grew, I think, quadratically with the square. And we can go to numbers of individuals way beyond 5,000. You might need a lot of computer memory to do this. Well, still, linear with the number of people. So we can actually run FaST-LMM on the same data that we've been playing with. So we read that same data set we've been reading over and over again. We read a phenotype file. In this case, it's just a string because this version of FaST-LMM doesn't use my pheno reader yet. There's a covariate file, which is things that aren't genetic that you want to factor out, like usually it's things like sex of the person and age. We bring in one of our GWAS functions. And all we do, it looks almost the same as that linear regression thing we called before from the standard library. So we pass in SNPs, which is from our bed reader, our phenotype file, our covariate file, and we get a result. Whoops. Running. And it says the SNP with this name has a p-value of 3 times 10 to the minus 23rd. So that seems pretty good. And likewise, a bunch of these other ones look pretty good. One thing I'll just say in passing is even though we don't use pandas for our main data processing, we love using pandas for this kind of outputty stuff. Things that we normally would have written a text file and then maybe brought it up into Excel to do some last minute things. We write it to pandas format and then do all those kind of spreadsheety things inside pandas. And this we can look at graphically. There's a kind of chart common in Genome Wide Association Studies. So this is all, and on the synthetic data set, this is all 5,000. There's a point here for all 5,000 positions along the DNA and the data that we had. And here is the statistical significance of whether or not there's an association between that location and the trait we gave. You can see most of them are down here. This is 10 to the minus 5th, but there are 4 that are higher than 10 to the minus 5th, including one way up there, 10 to the minus 23rd. So FaST-LMM, in the past, it originally only worked with bed files, but now it'll work with any SNP reader. In fact, you can also pass it a string, and if you pass it a string, it'll say, oh, this is a string, I'll use the default reader, which is the bed reader. And you can pass things in memory now. Internally, we do that IID intersection, that case intersection. We do standardization. We do indexing by property. We stack things. We use all the features that we saw demonstrated. I have a version, but it's not public yet, that uses the phenotype reader. So that makes it easy to swap dependent and independent data instead of assuming that one is always associated with a particular file format. And I've got a version that uses the kernel reader. When we run on a cluster, it was spending like 6 minutes before it did any work reading things from a slow file format or recomputing. And I've used the kernel reader to write that fast NPZ format out, distribute that to the cluster, and that loads up like in seconds. So I thought I would end the talk with just a general discussion about why we use Python. I'm not really any more of an expert on this than anybody else who's been using it for a while. So let me just share my experience, and you can agree or disagree or add your own comments. So 2 years ago, we had a refereed journal paper basically rejected because we gave our algorithm free, open source, but it was in C# instead of Python. And the referee just didn't want to find a Windows machine to run it on. Now, if we'd really wanted to, we probably could have gone back to the editor and said that's unfair. But sometimes when somebody tells you something unfairly, you should listen to them anyway. Because the referee did us a favor by telling us that our audience was much smaller because we were using, writing our scientific algorithms, our genomic algorithms, not in Python. We switched to Python, and we're getting much better uptake on on the things that we produce. Another advantage, and I think it's the other part of it, is we don't have to write everything ourselves. We wrote our own, or wrapped our own linear regression before, logistic regression, cross-validation, all that when we were doing things in the other language. In Python, there are already beautiful toolkits that you could have learned about in the other tutorial to do all those things. And you save so much time by not having to write every library yourself. If you need to read bed files, hopefully you'll use my library and you won't have to do it yourself. There's also all kinds of auxiliary things, testing packages, code coverage testing, API documentation, auto-generation, which we use for this library. Somebody's already figured out how to do logging, and you can just use the logging package. It's really worked that people can use our tools as components and not just standalone programs. Yeah, people did use our previous programs, but they always would just run it at the command line with a text file, get a text file out, and that would be done. They would never use it as a component in their own program. And that's what we're getting by using the two-way community that Python provides. So now I'm going to criticize the language itself, but everything else is secondary to this social phenomena, which is people share things. Yeah?
So 2 years ago, why didn't you pick up R instead of Python?
That's an interesting question. In our community, most people were using Python. My personal opinion is that R and Python are very similar to each other. So I can't really recommend one or another. I think they both have almost identical feeling of community and shared libraries and components. So
there's great resources on the web that talk about this. I've seen a couple websites that compare R with Python. So
don't you think the real answer, though, is you should find out what everybody else in your community is already doing and just go with that?
and it's also what you want to do. They have different strengths.
I should say I've only used R for a few projects. I like Python better than R, but that's just me. I'll talk about some of those in a second. So I'm stealing this from a book, but not about programming languages. I think Python is a wonderful, terrible language. So it's wonderful because it has these MATLAB-like slicing and indexing things that we saw PySnpTools adopt. But that works for matrices, and it works great. Except it's inconsistent. So there's a thing for HDS. So for just NumPy arrays, you can't do lists of indexes on 2 dimensions at once. So you end up having to do it on one step and then another step, and you've just doubled your memory usage for no good reason. In HDF5, there's a way to read rows or columns by indexes, but your indexes have to be sorted. And if they're not, you just get an error, and you probably never even knew that rule until you broke it. Like when exactly NumPy will make a copy of something versus a NumPy array versus creating a view, even the documentation doesn't tell you. You just kind of have to look. And if you try to look, it doesn't even promise that when you look at those flags features that will always tell the truth. I think it does, but it doesn't. This language doesn't promise that it does. One of the things I really miss from C# is refactoring is much worse in Python. So in C#, if we started with just kind of an ad hoc reader that, say, returned a dictionary with IIDs and an array, and then later we decided to make it into some kind of class, we would just take some part in our code that generated the reader and replace the dictionary type with our new class type, say, SnpReader, and then we would just get compile errors. We'd get like 20 compile errors from everybody who used that reader. And we would go to those 20 places and we would fix it. And we would compile again, and now we'd get 40 errors from every place that used those. And we'd fix those, and we'd do that 3 or 4 more times. And after that, there'd be no more compile errors, and every single place in our code that used to assume that our bed format was a dictionary would now be guaranteed to know it was using our new fancy class reader. In Python, you change your reader to output something new, and you don't get any compile errors at all. Everybody's happy. And then you run, and you get a runtime error, 1. And then you fix that one, and then you run again, you get another runtime error. And after a while, they become less frequent, but you have no idea that you've ever found the last one unless you have 100% code coverage testing all combinations of types. So that's too bad. It's wonderful. Our old code had to run, we were always using the latest version of C#, so it wouldn't run on other versions of, open versions of C#. With Python, I develop on Windows, but most of our users are probably running it on Linux, and we know people run our code on Macs too, and everything works fine. There's a little bit of terribleness, like you're all happy, and then some library you uses deprecates something or removes a method, and then you didn't do anything, but your code doesn't work anymore because a library got updated. This one kills me. Python style is stupid. So this is just the coding standards of Python. This has nothing to do with the language. It's sad. But there's a rule that says abbreviations are okay, but you don't have to do it. Modules should be generally, that's normally like file name things, are normally lowercase without underscores, but functions are lowercase with underscores suggested, but not required. You'll still see constants with all caps. And all this is to avoid camel case, these cap words, but your class names should be cap words. So, I don't know, it's just the way it is. Did I miss? I may have forgot to say this, but I didn't say it here. Well, okay, here it is. A bunch of wonderful things. I love multiple return values. I don't know why, I mean, just every language should have them. Python's probably the most readable language I've ever seen, and I've worked in languages like APL, which have a reputation for being the least readable languages that in existence. I see much less redundancy, especially compared to C++, not having to have header files and all that stuff. I love, unlike Java or C#, you don't have to make everything an object if it doesn't need to be an object. Print hello world is a completely fine program, and why should it be any more complicated than that if that's all you want to do? On the terrible side, Python is single-threaded almost fundamentally because of the way it's architected. Independent of that, it seems, yeah.
I've been using the concurrency package.
I'll have to look more at that, but okay, here's the 2 problems. So we use MKL library to do our matrix stuff. So when we do our matrix operations, eigenvalue or matrix multiply, all our processors get used and we're completely happy. I should probably look at the concurrency to see what it does, but I understand there's a global access lock. That means things aren't.
If you do process, but not if you do threads.
Okay, I'll have to look at that more.
There's a process factory and a thread factory. Right. But I still haven't figured out how efficiently it pushes the threads across CPUs. That I'm not positive of. It does some.
So I know there's going to be another problem that's going to make it hopeless. In C#, C# got multi-threading at the same time its libraries were created. So all its libraries are thread safe. Python, even if some people are using a concurrency package, none of us library writers are writing for concurrency, which means you'll never be able to use anybody else's code and be sure that there's not some threading.
Actually, one package I'm using for connecting to MySQL does say you can use the package across everything, but open a new connection per thread, which is fine.
Yeah, I'll have to look at that. For things like file write, there's often times you'd just like to be able to be writing on multiple threads.
That would not fine. You're right.
Okay. But when you're doing lots of matrix operations, you're still okay because you can use things like the NumPy MKL library from Anaconda for whatever their inexpensive license is. I like that you can script anything. I've had scripts from Python that called C# and PowerShell and Hadoop. That's just on the Windows side. So I just know that anything that can be scripted in Python. I'm sorry that it doesn't have true or enforced interfaces. The idea that you say that this is a PySnp PstReader, and you claim you're a PstReader, and if you're not, you'll get an error message at compile time instead of a runtime error. I've had a thing where someone wrote code for arrays, and we passed in an array, and it failed. And it failed because they wrote it for NumPy arrays, and I passed in a regular Python array. And things like equality have a different definition between NumPy arrays and regular arrays. So they're almost, the two data types structures are almost the same interface, but not exactly the same. So that, to test that, you have to have all kinds of, to basically test all combinations of your types. There's a flip side to that, though. Java is terrible. They defined the stream class, and then they closed it so no one could inherit it. So then someone defined a new stream class, and that one's probably closed. So if you want to make something that people, a generic thing that people read from, it won't work with any of the standard methods. In Python, if it's got duck typing, right? If you make something that knows all the methods of stream, or at least all the ones that are used, it's a stream. Likewise, what other language even had the idea that you could create a whole new array class and have everything mostly work, like a NumPy array? So that's pretty sweet. And SnpReader, any of these classes, I can't stop you from making your own version of it, and we enjoy that freedom. So in balance, the wonderful is much better than the terrible. More than good enough. Community makes the difference. Someday I'd love to see a language that's like Python and readability and some of these other features. Maybe has type inference. There's some cool stuff going on in C++ where they're doing things where they make sure something follows, say, list semantics, but it doesn't have to inherit from list. That's concepts light. So maybe someday we'll have a language that's even better, but I'm pretty happy where we are now. I also think we can mitigate some of the terrible by making better names when we're doing our styling, names of variables and things, do more testing. And I think since we need to exploit the features it has this wonderful slicing and stuff. You know, if that's appropriate for your problem, use it. Don't be afraid to use its cool features. Okay, we'll finish a little bit early. Then we have questions, I guess. In conclusion, PySnpTools is open source. It's on GitHub and PyPy. SnpReader is used by at least 3 projects, only one of which I'm intimately involved in. I'm peripherally involved with another. I hope we'll see that the PstReader generalization, where we have this matrix data that we don't read until we need it, but we also have rows and column labels and properties, is a nice way to get the full efficiency of NumPy arrays, because they are NumPy arrays when we actually read them, versus some of what you get from Pandas, which is you have row IDs and column IDs and some properties, and you don't lose track of that this row goes with this person. If you work with genomic data like bed files and phenotype files, please use this. I think undeniable you should use this. If you work with other data of this type that's not genomic data, I hope you'll consider using it, even if you have to do something like make a low memory random access reader yourself before you can use the rest of the infrastructure. And I'm available for any questions.